I have a coil that has 265 turns per centimeter, and across the coil I've attached two light-emitting diodes, a green one and a red one, and they are connected such that if the green LED is forward biased, the red LED would be reverse biased. Here is a schematic of our setup. We have our coil, and attached to the ends of the coil are our two LEDs. And they're attached such that if the green LED is forward biased, the red LED is going to be reverse biased. And we're going to take a magnet and drop the magnet through the coil. I have a magnet that I'm going to drop down the center of the coil. Now let me do it again. You saw the LEDs come on, but watch closely and you'll see that the green LED comes on as the magnet starts to fall in, then it turns off, and the red LED turns on as the magnet is leaving the coil. Let me do that one more time. This behavior can be explained with Faraday's law, and it's referred to as electromagnetic induction. As the magnet falls and enters the coil, there is an increase in magnetic flux inside the coil. And as the magnet leaves the coil, there is a decrease in magnetic flux inside the coil. I often ask a homework or an exam question that's similar, except the magnetic field region is stationary and a circuit moves into and out of the magnetic field region. Here I have a magnetic field region that is 2 meters by 2 meters, and let's assume the magnetic flux is coming up out of the page. I have a circuit over here that is 1 meter by 1 meter, and it consists of wire and one resistor. We're going to have the circuit moving in the x direction at a constant velocity, so imagine 1 meter per second. Lenz's law is a qualitative description of electromagnetic induction, whereas Faraday's law is a quantitative description. We will use Lenz's law to understand qualitatively what happens as our circuit moves into the magnetic field region and then out of the magnetic field region. This will also help us to understand the statement of Lenz's law. Lenz's law states that the induced current is always in a direction to produce a magnetic flux that opposes the change in magnetic flux that produced the induced current. Let's look at our circuit moving into and out of the magnetic field region to understand this statement of Lenz's law. As our circuit moves to the right, we want to focus on what is happening to the flux inside our circuit. As our circuit is moving, at first there is no change in flux inside the circuit. That changes as it starts to move into the magnetic field region. Let me depict the magnetic flux coming out of the page with these dots. So as the circuit moves in, it's overlapping more and more area of magnetic flux, so there's more and more magnetic flux coming out of the page within our circuit. Since the magnetic flux out of the page in our circuit is increasing, Lenz's law tells us that there will be an induced current to produce a magnetic flux into the page inside our circuit. We know if we point our right thumb in the direction of the current flow, our fingers will curl around the wire in the direction of the magnetic flux. So if we have a current flowing clockwise, then the induced magnetic flux will be into the page inside our circuit. As the circuit moves into the magnetic field region, we will have an induced clockwise current flowing in our circuit. Once the circuit is totally inside the magnetic flux region, there's no change in the magnetic flux in the circuit, so there will be no induced current until it starts to leave. Now, as it's leaving, the amount of magnetic flux coming up out of the page inside the circuit is decreasing. Lenz's law tells us there will be an induced current to produce a magnetic field to resist this decrease in magnetic flux inside the circuit. So a counterclockwise induced current will flow because if you put the thumb of your right hand in the direction of the current in these wires, your right fingers are coming up out of the page inside the circuit. So the induced current produces a magnetic flux out of the page inside the circuit as the circuit leaves the magnetic flux region. Once the circuit moves out of the magnetic field region, there is no longer any change in the magnetic flux through our circuit, and so no induced current. If we consider a clockwise current as positive and assume that the circuit is moving at 1 meter per second and at t equals 0 is when it starts to enter, we will have a clockwise current flowing as shown in the graph. At 1 second, the circuit is totally inside the magnetic flux region, so from 1 to 2 seconds, there will be no current flowing, and from 2 to 3 seconds, there will be a negative current flowing, in other words, a counterclockwise current, after which the current will be 0. Let's go back to the situation where we had a stationary coil and we dropped the magnet through the coil. The direction of the current flow can be determined by which LED turns on. If the current is flowing out the top of the coil, the green LED is forward biased and turned on. If the current is flowing out the bottom of the coil, the red LED will be forward biased and turned on. As the magnet was falling into the coil, the green LED turned on, indicating that the current was flowing out of the top of the coil. As the magnet was falling out of the coil, the red LED turned on, indicating the current was flowing out of the bottom of the coil. As the magnet falls into the coil, there is an increase in magnetic flux pointing downward inside the coil. I've added a core so we can visualize the windings. Of course, there is no core so that the magnet can actually fall through the coil. Lenz's law tells us that as the magnet starts to enter the coil and there's an increase in magnetic flux pointing downward, there will be an induced current in the coil to produce a magnetic flux pointing upwards. To produce a magnetic flux pointing upward inside the coil, the induced current has to be flowing as shown, which means the green LED will be forward biased and turned on, and the red LED will be reverse biased and turned off. As the falling magnet leaves the coil, there is a decrease in the magnetic flux pointing downward inside the coil. Lenz's law tells us that there will have to be an induced current to produce a magnetic flux pointing downward inside the coil. So the induced current will have to be flowing as shown, which means the red LED is forward biased and turned on, and the green LED will be reverse biased and turned off. Faraday's law, shown here, is a quantitative description of electromagnetic induction. I have another video that shows how you go from experimental observations to Faraday's law. I will not do a direct application of Faraday's law to our magnet falling through the coil. If you want to look at something similar, look at my video on transformers. I do want to point one thing out looking at Faraday's law. This psi is the magnetic flux, and we've been talking about how the change in magnetic flux is driving this induced current. Looking at Faraday's law, we see this N multiplying our change in magnetic flux with respect to time. This N is the number of turns in our circuit. So N times psi is something called the flux linkage lambda. And it's really the change in the flux linkage that drives the magnitude of the induced current. In the example we looked at of this circuit moving in and out of our magnetic field region, our wire attached to our resistor went around once. So we would use an N equal to 1 in this case. If we had attached a wire to one end of the resistor and looped it, say 10 times, and then attached it to the other end of the resistor, we would use N of 10. And what would happen is that the current would be increased by a factor of 10 from what it was with just one turn. Where that would come into play in our example of a magnet dropping through the coil is the number of turns of the coil per unit length. The greater the number of turns per unit length, the greater the induced current as the magnet drops through the coil. If you wanted to replicate this experiment, including winding your own coil, make sure you wind at least 265 turns per centimeter to get results that will be comparable to what you saw in this video.